Here's integrated 3, it's problem 9-81. It says when the rabbits were first brought to Australia, they had no natural enemies. There were about 80,000 rabbits in 1866. 2 years later, in 1868, the population had grown to over 2,400. Letter A, why is an exponential equation a better model for this situation than a linear one? Is a sine function better or worse, and why? So it turns out that, well, just to answer the first question, exponential growth, like here's an exponential model right here. The graph, it gets steeper and steeper as you go up, and we use that graph. You should just have experience with that when things like double every year, or if they go up by a percentage or something, then the graph gets steeper and steeper, and that's exponential model. So population growth is always modeled with a exponential model. A linear model wouldn't exactly make sense because it would just go up at a steady pace. But when rabbits multiply, it's like you start with 2, and then each of those 2 have, well, they have more than 2 more, but each one of those rabbits have babies, and then all their babies have babies, and then all their babies and babies are having babies, plus the original 2 rabbits are still having babies. So it's going to steepen, like it's going to grow more rapidly as time goes by, where this model, the linear model, doesn't really work so well, because this would be if it just had a steady growth, but that's not really a good model for population. And sine could maybe model some growth maybe around a certain time period, but you'll see that a sine model, that works best for something that's going up and down and up and down. So we're going to say that the exponential model works best for letter A. And then it says letter B, write an exponential equation for the number of rabbits. So the exponential equation is y equals, let me write that, the exponential equation is y equals a times b to the x. And if you're not familiar with that, a is your starting amount, and b is your growth factor, your growth multiplier, and x is time. So I'm going to start out with 80,000. So I'm going to let x be 0 in 1866. And then I'm going to plug those, well, I'm going to use the 80,000 for A. Did I show that yet? I didn't. So I'm going to say I'm going to plug in an x and y, an ordered pair here. And so I already did. So here's this other ordered pair. They said in 1868 it was 2,400,000. So I'm going to use the 2 as an x because it's 2 years later. And I have my y. And so I plugged this in for y, and I plugged this in, the 2 in for x. And I got this. And then I'm just going to solve that for, I want to find out what b is. And so b squared is going to be, well, I can get rid of some of these zeros. 240 divided by 8. Well, 8 times 3 is 24, so 8 times 30 would be 240. Square root both sides. And so b is going to equal the square root of 30, but I put it in my calculator, and the square root of 30 is 5.477-ish. So now I'm going to write my new model, because I had to do this work right here to find out what b was. So y equals my starting amount, which was 80,000, times the growth factor. So they're growing pretty fast to the x. This is my exponential model that models the growth of the rabbits. And then, so for letter Letter C, it says, how many rabbits does your model predict will be present or were present in 1871? So I used 0 for the year 1866. So 1867, 1868, 1869 would be 3. 1870 would be the 4th year. 1871 would be the 5th year, I think. So I think 1871, I'm going to use a 5 here. And we'll just see what that gives. So I already have the number in my calculator, so I'm going to raise it to the 5th. And then I'm going to multiply that number by 80,000. Oh boy. And so that's about, well, let me write it down first. 394. That's about 394 million. I'll just say 394 million. That's a lot. And then letter D says, according to your model, in what year was the first pair of rabbits introduced into Australia, and is that reasonable? So the way to figure that out is I would, when the first pair showed up, I could say y is 2. That's because y is like the amount of rabbits present. And it's going to give me a negative number. I guess I'll go ahead and do all this. And then I can subtract that. Well, we'll see what happens when we get there. Okay, so let's see what this number is. 2 divided by, oh boy. Okay, so this number ends up being, well, it's pretty gross. 2.5 times 10 to the negative 5th, and then I'm just going to leave that in my calculator, and I'm going to divide it by, oh wait, no I'm not. I'm going to, I got to solve for x, so I need to log both sides. Kind of gross. And then there's a log law that says the x can come down out front. And now I can divide both sides by log 5.477. And so x is going to equal, let's see, I've got that already in my calculator, so I'm going to log it, and then I'm going to divide by that. Okay, so let's see, log answer, and then I'm going to divide by log of 5. So I got x is about negative 6.23 years ago. Or so I can like subtract from 1866. I can subtract and say that, well, that's a little over 6 years. Sorry, that's a little over 6 years before 1866. So I got like 1850, sometime during 1859. I'm just going to say, because it says, according to your model, in what year was the first pair of rabbits introduced into Australia? And is this reasonable? Well, I'm going to say it must have been sometime in 1859. I'm going to have to cut this recording off because I've reached my time limit. So we're going to say, well, I think that seems okay. Letter E, I'm going to just show it to you because I have to end this video before my time limit expires. So I'm going to just let you read that and see if you can make sense of the rest of it. All right, good luck.